So we welcome now Leo Perrin from INRIA, who will talk of what happens when you don't have tools for the case of algebraic cryptanalysis.
Thank you for the introduction, and thank you for having me here. I will start with a small apology to the students in the room who attended my class of yesterday, because there will be quite a bit of overlap. So a lot of this should sound familiar to you, but hopefully not to the rest of the audience. So when I was invited to give a talk here, they wanted me specifically to talk about the tools that are needed for algebraic cryptanalysis. And it happens to be a topic I have opinions on, because so far we basically don't have any, and that was a huge problem. So it got me thinking about what is a tool in the first place. And the way I organized my thinking about this was not so much based on the tools I wish I had, but on the observations I made from the absence of tools. So I'm going to start with my conclusion, which is how I'm going to define a tool in the end. And my point will be to convince you that this is a sensible definition. It's a convenient abstraction layer above a specific know-how. So it's not really, it's like, for instance, when you do some differential cryptanalysis, you need to find the differential trail. You need to invent the key recovery part. And the problem we have right now is that it's less and less the case. But even just 2 years ago, it was very like artisanal, I would say. So like more like a trade than a science. Like we can teach people how we do it, but it's not easy to reproduce, and it's more a skill than a science. So in this talk, I'm not going to talk, I'm not going to talk about the tools I'm happy with. I'm going to talk mostly about the tools I don't have, or at least that I didn't have at the time when the research I'm going to talk about happened. So first, I'm going to talk about the case of algebraic attacks, and then I will move on to the more meta discussion about what is a tool, but I will spend more time in the first section. So on algebraic attacks, my apologies. I talked for 6 hours yesterday. My voice has opinions about this. I'm going to start by motivating the need for algebraic attacks. Then I'm going to describe how they work and how, in particular, some specific type of algebraic attack has been very devastating. That was presenting like a very devastating algebraic attack that was presented at last crypto, and what I have learned along the way in light of this attack. But first, the motivation for the relevance of algebraic attacks is these symmetric techniques for advanced protocols. So I'm guessing you all know what the purpose is for cryptography in general when we operate on data, because that's usually what we care about, especially in symmetric crypto. We try to secure data when it's at rest or in transit. So we want to provide the 3 usual guarantees: confidentiality, integrity, authentication. I'm not going to spend too much time on this slide. But what's happening now is that people from other communities are starting to, well, started for a while, to invent protocols that can secure whole computations, not just the data, but the computation itself. So for instance, in the case of FHE, fully homomorphic encryption, what they allow is the evaluation of a function despite on some data that is encrypted. So you encrypt your data, you send it to a server, the server does some operation, sends you back the result, you decrypt it, and it makes sense. So the whole communication, the whole computation made by the server has not allowed the server to obtain any information about your data. For MPC, MPC is a very, very broad term. It means that multiple parties need to work together to evaluate a function. This has a ton of applications, from specific signature schemes, when you invent yourself a split personality and do some MPC between you and this other person living in your head, and you can build a signature out of it, like a picnic. It can be masking, good old masking, side channel countermeasure. And then you have all the ZK, so all the zero knowledge proof arguments, all the ZK, snarks, darks, all that kind of things, where the idea is that you're going to prove that you know something or that you have done something without revealing the something. So all of these come from the public key world, but all of these also need symmetric primitives inside them. The symmetric primitives that are going to be intended to play well with these protocols are often called arithmetization oriented, and they are all lumped together in this big category. Kind of yes and kind of no. So all these protocols, first, there are families of protocols that have different instantiations, and each of them might need a specific type of symmetric crypto that plays well with this specific protocol. But it is true that often they are arithmetization oriented. So what does that mean? The meaning is not that it's more complicated than it looks, because an arithmetization will depend on the arithmetization you use will depend on the protocol you're using. And there are many different arithmetizations that are not really compatible. So really here, I want to emphasize that I'm painting with a very, very broad stroke. But for instance, if you look at R1CS, it's a specific type of arithmetization that is relevant in some ZK protocols. In this case, the way you're going to arithmetize the computation of y as being equal to this expression, so c times ax plus b to the power 10. This is just a basic computation, and you're going to arithmetize it, if you want it to play well with your ZK protocol, in the following way. So you're only allowed in this case to use straight line programming. So all your operations can have only 2 operands. So it forces you to introduce intermediate variables. And the way you're going to perform this computation is that first you're going to compute the product of your input x by the constant a. Then you're going to generate a new variable, which is equal to this quantity where you added b, etc., etc., etc. And then in the end, you can check y will indeed be equal to c times ax plus b to the power 10. This is a form of arithmetization. There are many others. In this case, what you also need to keep in mind is that when you make an arithmetization, you also have a cost function associated with it. For the specific case of R1CS, multiplication by constants and additions are basically free. However, multiplication costs you. So here it would cost you 4 of these R1CS constraints. Very sorry about this. What you need to remember is that the way you're going to turn your computation into an arithmetic circuit will depend on the specifics of the arithmetization you're using, which in particular will depend on the operations you're allowed to use. So here you have field operations over a field that I have not specified, but it has to be there. And the cost function itself will also depend on, again, on the arithmetization you're using. So for R1CS, you care about the number of multiplications. If you're looking at something called Planck, you also care about the number of additions. They are not free. They also cost you. However, and that's something I'm going to rely on for the rest of this talk, very often what you want is for your arithmetization to have a low degree. You want to minimize the number of multiplications. That's the metric you use to evaluate the performance of your scheme. So it's going to have an efficient arithmetization if the arithmetization involves few multiplications. It's not always sufficient, but it's usually something you care about. But this will have consequences. So I'm just going to quickly go over, because I really want to emphasize that this arithmetization stuff can be very broad. So you have these 3 families of protocols, MPC, FHE, ZK, that I have lumped in this category of advanced protocols, whatever that can mean. And so these are some of the protocols that fit in these categories, or the primitives that fit in these categories. So MPC, you're going to have the protocols that are intended for masking. You will have the MPC in the head that you can use to do signatures. They need pseudo-correlated functions, which are something, again, completely different. They need verifiable delay functions sometimes. So it's functions that are just super slow on purpose, but for which checking that the output is correct is fast. Hence the verifiable part. For FHE, I have put 3 different FHE schemes here, BGV, FV, and TFHE. And for zero knowledge, you have many different arithmetizations. So I have talked about R1CS before. I quickly mentioned Planck. You also have AIR. You have many, and they come up with new ones every day. The arithmetization-oriented category basically is this blue potato thing. So in particular, these PCF, VDF, and TFHE don't really fit in here, but it contains a lot of stuff. So while yesterday I made a point to say that it doesn't contain everything, today I will also point out that it does contain quite a few things. There is a pretty important distinction in terms of design and in terms of cryptanalysis. It's the difference between primitives that are intended to have an efficient arithmetization of the evaluation and the protocols where you care about the arithmetization or the efficiency of the arithmetization of verification. So what's the difference? What I call evaluation is just you know the input, x, and given x, you will put x in some arithmetic circuit that you will go through, and you will get y. That's the arithmetic circuit that's used for evaluation. For masking, for instance, it's pretty straightforward. You have your block cipher, it's masked, you have the plain text, it's your input, and you want that the function that maps this input to your output corresponds to a simple arithmetic circuit with few multiplications, because the multiplications cost you when you mask. But you also have the case of verification. And that's going to be pretty important later because I'm going to focus on this one. In the case of verification, you know both x and y. So you don't need to check that to evaluate an arithmetic circuit given x to obtain y. You already know x and y, and you want to check that the verification, that a specific relationship between them holds. For instance, if y is equal to the cubic root of x, if you are going to evaluate this expression using an arithmetic circuit, it's going to cost you a lot because the cubic root corresponds to a monomial with a huge exponent. Because the inverse of 3 modulo, I don't know, a prime, the p-1, where p is a prime of 256-bit length, is going to be an enormous number. However, if you have that y is the cubic root of x, you also have that x is equal to y cubed. And in the case of verification, you know y. So instead of checking that y is equal to the cubic root of x, you will check that x is equal to y cubed. This is only relevant in this case because what you're doing is verification and you know both the input and the output. And you have an implication here. If you have an efficient arithmetization of evaluation, you will, of course, have an efficient arithmetization of verification because you will just, to check that the relationship between y and x holds, you will just evaluate the function on x. It will be efficient because you're in the brown part. And then you check that you indeed get the correct output. But this can be very different. The green part does not imply the brown part. Very quickly, I will mention these other techniques that do not fit nicely in this arithmetization-oriented framework. So just so you remember that it's not as simple as symmetric crypto for advanced protocols equals arithmetization-oriented. So these pseudo-correlated functions, there are strange functions that have started to pop up in the literature that are used at the start of some MPC protocols that are extremely strange. Very often they are quadratic. They have huge inputs, teeny tiny outputs, and a strange security model. It's something we as a community, the symmetric community, should look into, I think. The case of TFHE, it's kind of, well, the cost model is completely different. I'm not going to go into, but it's not really arithmetization oriented. In particular, in your graphs of the computations, you can have loops. And the verifiable delay functions are really their own thing. Not going to talk about them, just mention that they exist. And they can sometimes use symmetric techniques as well. Where it becomes really weird is beyond the fact that you want to have your low degree arithmetization, be it of the evaluation or of the verification. This arithmetization will be defined over a specific mathematical structure. And that's going to change. You will see there are many different ones. Well, I will just show them all at once. For masking, which I'm guessing is the case that is the most familiar to this audience, you're usually in F2. So you're over bit string, so F2 to the power n. And that's the mathematical structure you work with. Although recently some papers have started to argue that maybe the masking should be done in FP. So you have some algorithms like small p square, which are block ciphers that are defined over Fp to the power n, so over vectors of elements of Fp, where p is equal to 127. For FHE, they usually work over rings. So these rings can be fields, but they don't have to be. And these protocols, they can be defined over F2 to the n. Sometimes they're defined over Fp. And when they're defined over Fp, this p is going to change a lot. So it can be the scalar field of an elliptic curve, so it's going to be 256 bit long, the value of p. Or it can be p's that were chosen specifically to play well with some protocols, more like the Goldilocks prime that is used very often, which is 2 to the 64 minus 2 to the 32 plus 1. It's just 64 bit long. And now they are moving to even shorter primes. So the Mersenne prime, which is going to be 2 to the 31 minus 1. My point here is, well, I have many points I want to make with this slide. First, many of these correspond to this arithmetization-oriented paradigm. And for most of them, you care about the degree of the arithmetization. So you're kind of forcing yourself to have low-degree equations in your primitives if they're supposed to play well with these schemes. My second point is the variety. So you have Fp for very different values of p, from 127 for the block cipher intended for efficient masking in hardware to 2 to the power 256 plus minus epsilon for some of the primitives that are here, which is going to be annoying and which is going to be a reason why I think we really need to have some automated tools for the cryptanalysis of these things. So now that I have set the stage of the context, sorry, let's have a look at the symmetric ciphers that are symmetric primitives that are intended to play well with these schemes. So these arithmetization, often, in order for them to be considered efficient, they need to have a low number of multiplications, be it the evaluation or the verification. Again, oversimplification, but let's work with that for now. So the primitives that are going to be have efficient arithmetizations will often use monomials, an x to the power d, where you try to keep d small, or at least, yeah, let's go with d small. They can have, on the other hand, big diffusion matrices, because often the additions are much cheaper. And in the case where what you care about is the arithmetization of verification, they will be using often the inverse of small monomials, the compositional inverse. And it's going to look like this. For example, this is Griffin. The picture is from the thesis of Clémence. And it's the nonlinear part of, it's just the nonlinear part of Griffin. Griffin is a hash function with, which is optimized to have an efficient arithmetization of the verification. So you have your small monomial, your inverse of small monomials, and these functions f2, f-1 are quadratic. So that's the kind of stuff we talk about sometimes when you talk about arithmetization-oriented symmetric primitives. Okay? But this talk is not about how to design arithmetization-oriented primitives. It's about tools, and in particular tools for algebraic attacks. So the problem we have is that in order for your primitive to have a low degree arithmetization somewhere, it means that there is a low degree arithmetic circuit that's going to connect the successive internal state of your symmetric primitive. So as you go through the rounds, the value at round r plus 1 will be connected to the value at round r by some low degree arithmetic circuit because of the requirements implied by arithmetization orientation. But if you want to do an algebraic attack, as an attacker, what you want to have in a primitive is that there exists a system of low degree equations that can model the evaluation of your primitive, so that you can write a system of low degree equations that completely describes how your primitive is running. It's basically the same thing. So what you want in your arithmetization-oriented primitive, in order for your arithmetization-oriented primitive to be efficient, it basically needs to be vulnerable to algebraic attacks, which is annoying. If you enable a low degree arithmetization of verification or indeed of evaluation of your primitive, this is going to imply a potential vulnerability to algebraic attacks. That's why algebraic attacks are much more relevant in this arithmetization-oriented world than in the usual world. For the AES, people have tried to algebraic attacks. Doesn't work so well. Here, it works extremely well, as you will see. But how do they work? Because so you have your system of low degree equations that's implied by the fact that you want to have a low degree arithmetization of verification, for instance. But what are you going to do once you have that system? And what tools are you going to use? Because as you will see, these can be problematic. So if you want to first you just need to write down your system of equations. For this, usually we use Sage, which is open source, usually works pretty well, but is very slow. It can be very, very slow. Then, in order to be able to find the roots of this system, you're first going to compute its Grobner basis. So GB is Grobner basis. I won't go into the theory of Grobner basis. I did that yesterday. It takes a while. But so in order to find this thing that you need, you have some algorithms from the literature called F4 and F5. And these algorithms are great because they are the algorithms that make this approach possible. The problem is that they don't have that many open source implementations. Those that exist are not super efficient. And there is a very big efficiency difference between the public and the proprietary implementations. The one of Magma is much, much, much better than the one in Sage. Things are getting better. I'm actually in touch with people who work on this kind of topic, and they're really trying to provide better open source implementations of F4, F5, and all the other tools that are relevant here. Once you have your Grobner basis, you need to change the order. Again, I'm not going to go into what that means. It's an operation that you need to make on your Grobner basis. And there are tools to do that. And in particular, there is an algorithm called FGLM. For this one, I'm not aware of any really practical issues. The implementations are not that hard to come by, or they're not that hard to make. However, there is a lot of variance. FGLM is the first algorithm that could do this step, but there are many, many, many variants that can be extremely efficient in some contexts and very bad in some others. So it can be very difficult to figure out which one you should use for your attack. And finally, there is the final step where you just compute the root of the last polynomial here, because it's univariate, so it's much easier. And this is actually, this is really not a problem. Once you have reached step 4, you're happy. Both from theoretical algorithm standpoint and in practice, it's also not a problem. So when you do an algebraic attack, this is what you're doing. At least that's what we thought. First, you need to write down your system of equations. Then you find the Grobner basis of your system of equations. Then you change the order. Again, I'm not going to go into what that means, but you change the order of the monomials in your Grobner basis. And then you do some univariate solving. And already we had some issues with our tooling at this stage. But it got worse. So when you run the previous, this pipeline on trying to find, for instance, SKCAM attacks against your new arithmetization-oriented primitive, you observe that step 2 is the slowest. So that's what we did with Anemoy in particular. Finding the Grobner basis was super slow. And as designers, we are happy because what you want to have is to make what you want to do is to make sure that the attacks are super slow. So you try to bound the complexity of the second step. You make sure that it's going to be above 2128, and then you're good. Except when you're not. So what happened is that we have found a way to completely bypass this second step. So all this nice tooling we have, all the nice tools that I've described in the previous slide, actually, they are not that relevant anymore. So I'm just going to, I won't go into the details of how we did this or the subtleties of the results. I just want to put this table here, which roughly gives the complexity in bits of attacks against the some full round primitives. So Griffin that I showed in a previous slide, Orion and Anemoy are other arithmetization-oriented hash function. And you can see a lot of numbers that are under 128. And this is for full round primitives. And it has actually gotten worse since then, because the similar team has used a different approach to get even better results. But so my point here is that the tools we were using to estimate the security level of our primitive didn't work. In practice, they just didn't work at all. We have found attacks that completely destroy all the claims that were made. So everything is broken, but at least maybe we learned something, hopefully. And yes. So from a designer's perspective, because I was like in both seats, I was both involved with the free lunch attacks, but the free lunch attacks kind of broke one of my ciphers. So I had both perspectives. From my perspective, one of our main tools, Sage, did what it was supposed to do. It was very annoying that it was so slow at finding Grobner basis. So when we were trying to prototype our attacks, it didn't work so well. But it's OK. F4, F5, turns out we don't care. Yeah, it's very annoying that we don't have efficient implementations to play with. But as far as this is concerned, completely irrelevant. FGLM, we made our own. Don't care either. And this one, as always, for the univariate case, yeah, it does what it was supposed to do. This is nice. It's efficient. It's easy. It works. So what happened is that the attackers, it's not that we took the tools that we had. So this F4, F5, we didn't improve it. We didn't improve these tools. We just created entirely new ones, completely custom ones. So yeah, in particular, what we did is to find a technique to build dedicated monomial orderings that work really well. Feel free to ask me questions about it. But in particular, we the designers, relied on the assumption that this chain, so first F4, F5, then FGLM, then univariate root finding, was the only way to find the roots in your multivariate system of equations. And that is just wrong. Also, when we were trying to come up with an attack, both when we were designing and then when we were starting to attack the primitives, the lack of software, of efficient software implementations of some of these algorithms was very annoying, because it was hard to even just try to interpolate a complexity. So what would we have needed? So we would have needed both better ability to prototype our design attacks, and also a better interface with another field. So field here is not like FP, it's a field of research. It's the world of polynomial solving, multivariate root finding. So first, just writing down the equations that correspond to your to the attack you want to make is super annoying. It's very cumbersome. You're starting from scratch. Usually you don't even have a stage implementation of the algorithms. I'm told it's possible to figure these out using Rust implementations, but you would still need to do some work to get that working. So if from what I saw this morning, there starts to be tools that will output these equations, but they don't work in FP. Please make them work in FP. That would be great. And we didn't have the efficient implementation that would allow us to test our attacks. These chain, the F4 FGLM univariate root finding, relies on some assumptions, and which may or may not hold, which was a problem in our case. We wanted to use a very fancy variant of FGLM in our attack, which we couldn't, so we had to come up with a new thing. But also what we would have needed was a deeper understanding, basically to be better at multivariate root finding as designers. Because then we could have seen what was going to happen, and we could have seen the flaw in our reasoning, which was that F4, F5 would be super slow, so we would be safe. So what we needed was better tools. But what is a tool? So in the root finding case, sorry, harder to talk. Another issue we had was that this chain we used, the F4 FGLM univariate root finding, was invented by people who know exactly what they are doing, but it was intended to solve generic systems. And one of the mistakes we made was to decide that, okay, our systems are probably generic enough, so this is going to be the best. They are not generic enough. Our systems are super structured. When I showed them to people who work in this field, Magali Bardet, if you know her, she was very skeptical about the relevance of assuming this was the only way to solve our system. And she thought there could be a dedicated approach that's going to work better for us, possibly much better than this one. And she was completely right. And in fact, having a better knowledge of these steps and a better knowledge of how these things work, so by basically becoming better at multivariate root finding, is what allowed us to find the free lunch attack. So the one that completely bypasses one step. The good news is that I'm also confident that with this better knowledge, we can come up with better security arguments. So we will be able to also design new tools here. I'm going to explain a bit later. Now, I actually have a question for you, because I have never used MILP. But when you use MILP to find, I don't know, a nice differential trade, do you use a standard solving method, or have you looked deeper into how this MILP solver works, and maybe at designing your own dedicated MILP solving technique that works especially well for your problems? So is it something that someone has looked into? Yeah, Thomas. Okay, so I will have my answer. It's perfect. Well, nice. Because yeah, that's what happened in the root finding case. We had a deeper look at how they work, and we came up with our own that works best for our case. But still, as much as we would like it to be the case, we can't be expert in all fields. We do symmetric crypto. It's hard enough on its own. We can't also be experts at MILP, and experts at multivariate root finding, and experts at graph theory, and experts at whatever else we need. So we need to find the correct level of abstraction between hiding away some of the complexity from these other fields that we anyway will never be able to grasp, while still having enough fine-grained understanding of it that we can do these optimizations. But this correct level of abstraction is going to be very, very difficult to find. So the word tool, I've used the word tool a lot in these slides. Maria asked me to talk about tools, so I talked about tools. But what do we mean when we say we talk about tools? Because in the first case, we can say that MILP is a convenient tool to study differential trails. I think we all agree that this is correct. We should have tools that can convincingly say this primitive is secure. That's a bit too many E's, but the point still stands. The low performance of some tools prevented primitive designers from prototyping attacks. Specifically, I'm referring to algebraic attacks. This is what I explained in the first part of my talk. And we wished the tools to solve multivariate root finding problems were easier, at least as far as we are concerned, as people who are not super familiar with these tools, to understand and use. So what is the common thread between all these tools? The word tools here, what does it refer to? Because it seems like it refers to different things every time. Here, it's more like a theoretical concept of an algorithm. In point 3, it's really like a piece of software. Point 2, it's almost like a philosophical goal. What they all are, in my opinion, is a convenient abstraction layer above a specific know-how. It's what allows people to solve problems that would normally require advanced know-how to solve much more conveniently, much more easily. Like you're abstracting away the skills of someone or of a community. And for the specific case of root finding attacks and for the specific case of prototyping these root finding attacks, I have a bit of a wish list. So who knows if there is someone in the room who wants to help. As I said, I want to be able to generate and also to test the modeling of a round function using nonlinear equations easily. I want this to handle fields of many different sizes. As I said, small p square, p is equal to 127, 2-branch version of anemoy for, I don't remember which proof system, 2 to the 256 for the prime, give or take. So it needs to re-handle fields of many different sizes. It needs to be able to manipulate multivariate polynomials efficiently. So basic arithmetic, composing them, this Sage does. Reduction modulo and ideal, do it efficiently, that's very non-trivial. It needs to handle different monomial orderings. So as I said, there is some work being done by some colleagues on providing efficient implementations of F4 and F5, but they didn't care about custom monomial orderings, which turns out to be something super important. So I'm trying to convince them that no, it only matters to symmetric cryptographers working on arithmetization-oriented primitives, but we really do care. And finally, we also need to be able to estimate the complexity of some standard algorithms. So I want to be able to give equations to a tool. And if we tell me, in order to solve this, it's going to take whatever amount of time. And also, I wanted to suggest to me the best known algorithms for some problem. Because your FGLM, again, there are many, many variants of FGLM, depending on whether your system is sparse, depending on a lot of things I don't even know about. And there is a lot of progress that is being made, in particular by my students, which is about finding the correct algorithm in the literature. They are not coming up with their own, they are just digging up in the literature to come up with the best algorithm. Because we don't even know that. We, as symmetric cryptographers, we don't have access to this knowledge. We need someone or some tool to simplify access to this knowledge. How much time do I have? Two minutes. Okay, so I'm not going to go into that, but basically there is hope for security arguments at least. So I have come up with a theoretical framework that could allow us to find security arguments against root finding attacks. The key idea is that there is a quantity called the ideal degree. Not going to go into how it's defined, but it's a quantity that's an inherent property of the system. So if you play around with the Grobner bases, with how you compute them, doesn't matter, it's a property of your system. And if it's high, algorithms are less efficient. So I have come up with a trick that allows us to find lower bounds for this. So it means that we can use this to argue security. It's not tight. It's not going to give you an attack that matches the bound. In fact, it's not tight at all. I want to find a way to make it better in this regard, but there is hope. And my conclusion, so as I said, in my opinion, this is what a tool is. In the past, at least for algebraic attacks, we had big problems because we had no convenient approach to estimate attack complexities. So when we had our system of equation, we tried to estimate as best as we could the complexity of an attack against targeting this system of equation, but our computations were completely wrong because we didn't know what we were doing, basically. We had issues because of the lack of software tooling. A lot of time was wasted solving problems that are not interesting. It's not like a big algorithmic problem that you need to think. It's just an annoying thing that's standing in the way. But we had many of those. And we have performance issues. So Magma is super efficient for F4, F5 compared to Sage, but Magma is proprietary software, and then you need to find a license for it, and it's not cheap. And when you work at INRIA, you're not a university, so it's very annoying. But it's not hopeless. So at least to find the security argument, to build your security argument against algebraic attacks, some progress was made. And I'm trying to work with people from the math community to obtain better software tools to deal with these algebraic attacks, so that in particular, we don't need to try to extrapolate the efficiency of an attack from 2 or 3 data points, because that's annoying. And with that, I thank you.
Let's see if there is any question. Yeah.
So in the applications you mentioned at the beginning, are there any of them where the free lunch attack is either not the best or not that much better than the old way?
So the free lunch attack works particularly well when you're modeling, when you're in that box, basically, because you need to have these cubic roots or x to the power the inverse of a small quantity. Because what we do is we use, so you don't need to introduce new equations in your modeling of the primitive unless you hit one of these, because these have a huge degree. So then you need to introduce a new variable so you can do the trick of the indirect computations. And then the free lunch approach is that we use these specifically, and we make sure that these will be the leading terms. We build a custom order to make sure that these will be the leading terms in your equations, so that what we get is a Grobner basis right away. It's really relying on this idea of getting the Grobner basis for free right away. For the functions where the evaluation is corresponds to low degree arithmetic circuits, it doesn't work so well because you don't have this trick. Another issue we have is that the free lunch approach, the way we designed it, it's going to work really well when P is big, basically, because it can only work to solve your SKCAM problem to find 1 0 in the input and 1 0 in the output. So when you're in the case where P is 256-bit long, it's great because you have an attack. When P is 64-bit or when P is 31 bits, it's going to work in the sense that the algorithm will give you the output that you need, but it's going to take ages compared to just brute force. So there is also that. The attack here will probably just not work. And in this case, it will always work, but it will be relevant only for some sets of parameters. Did I answer your question? Perfect.
So in asymmetric cryptography, people use multivariate polynomials. People like try to use multivariate polynomials in asymmetric cryptography. Did you try to reach to them and share your knowledge?
So when I realized we were way out of our depth into this area, I realized I needed to get in touch with people from that community that could actually help us figure out what's happening, what are the best algorithms, et cetera, et cetera. And it just so happened that we had a student in our team, Pierre Rio, who was co-supervised by Jean-Pierre and by Magali Bardet in Rouen, and who was doing his PhD thesis on algebraic attacks against multivariate schemes. So we worked with Pierre for Anemoy. He did the simulations, and he was complaining that Sage is slow, and he had the magma he obtained somehow, so he used that. But then I started working directly with Magali. So Magali does exactly that. She does algebraic attacks against multivariate schemes. And I managed to convince her because recently she was looking for a PhD student to do algebraic attacks against symmetric primitives. So we are in touch. I was talking recently with Vincent Neger from Leipzig. So it's very nice to be in Paris sometimes because you have all these people nearby in other universities. So Vincent Neger is in Leipzig, and he's working on making good F4, F5 implementations that are open source in MSolve. And I had a discussion with him, and I said, oh, this is awesome. We really need it. And he was like, oh, awesome. You care about our work. It's really nice. And I said, yeah, can you make, do you handle weighted orderings? And he said, no, why would we do that? Well, because we need to. So I'm trying to negotiate. Hopefully we have that, but I'm not making promises.
I think we can, there's a question? Where? Oh, sorry. I didn't see you.
Yeah, thanks, Leo. Just wanted to say super nice overview, super nice talk. So implicitly, it seems you suggest so this order generation of designs that the community did seems less susceptible, like in MIMSI Poseidon, because they only have these low degree power maps, and nothing more innovative, basically. So, I mean, at the moment, it looks like they seem safe, but can you speculate as to what other new ideas could be around where these more robust designs could also be affected?
So speculating about the security of a primitive is kind of what we have to do when we design one, but it didn't work so well for Anemoy, so I'm going to be careful. In the specific case of Poseidon, first I'm going to advertise a talk that will be given tomorrow. So there is a workshop specifically on the cryptanalysis of arithmetization-oriented hash functions. And the first talk will be given by Guillaume Jazeron, who just started a PhD with me. And with his colleagues, they have found some very good attacks against Poseidon, precisely. And they had to use, so they did not invent it, but they had to dig up a recent paper where they started to use resultants for algebraic attacks. So it was a paper that was targeting Anemoy. And they managed to repurpose these to attack Poseidon, even though, as you said, Poseidon is in the brown box, while Anemoy is firmly in the green box, but they have managed somehow to make it work. And it worked much better than we expected. So speculating about security levels, I'm really not going to do that when I have students who have really literally come up with new attack techniques that they will present tomorrow. That being said, in my opinion, if I had to like if my life depended on the security of an AO primitive, which I hope doesn't happen by now because I don't think the field is mature enough, but let's imagine. I would go a different route, and I would say that what's important is to have something that's closer to what we know, which is instead of having a few words over big fields, to have a lot of words over small fields. So I would much rather use something that's defined for the Mersenne prime, 2 to the 31 minus 1, and then has 10, 20 blocks, 20 branches, rather than, I don't know, a two-branched version of well, Griffin doesn't have them. A two-branch version of Anemoy or of Orion, if they provide that. Because it's a completely different game to do that, and you become particularly vulnerable to algebraic attacks. So I think if I had to find a crude but hopefully efficient way to mitigate algebraic attacks, I would go for smaller fields, more elements. If that makes sense.
Let's thank Leo again.